5G NORMA is a EU-funded project within the 5G PPP initiative. It develops a novel, adaptable, and future-proof 5G mobile network architecture. The 5G NORMA consortium provides a good balance between network vendors, operators, IT industry, but also SMEs that focus on socio-economic analysis and demonstrations. The industrial competence is complemented by academic excellence in the area of network architecture research. The project started on the 1st of July 2015 and has a duration of 30 months until end of 2017. The project is coordinated by Nokia and Alcatel-Lucent is the technical manager. The network adaptability provided by 5G NORMA is enabled by means of 5 innovations that will be developed within the project. The network architecture developed by 5G NORMA is cloud-based. In the figure, we are only showing 2 levels of clouds, the edge cloud where the computing capabilities are close to the radio and the network cloud. The level of cloudification can be, of course, generalized. 5G NORMA has 3 enabling technologies. One is the software-defined mobile network control, which applies SDN principles to the mobile network-specific functions. Another enabling technology is adaptive decomposition and allocation of mobile network functions between the edge and the network cloud, depending on service requirements and deployment need. Last but not least, we have the joint optimization of mobile access and core network functions, localized together in the network cloud or the edge cloud. In the figure, we are using radio access network, core network, control and user plane according to the legacy terminology, but within 5G NORMA, the separation between RAN and core network is going to blur. The flexibility provided by the 3 enabling technologies allows the design of a mobile network architecture that natively adapts to different types of services, which have different requirements in terms of mobility, latency, traffic volume, security, and power consumption. It is very important to highlight that the flexibility of 5G NORMA architecture will not be limited to today's services, but will be capable of coping with next-generation services that pose new requirements onto the network architecture. 5G NORMA will further leverage the flexibility provided by the enabling technologies to foster novel mobile network multi-tenant scenarios in which the mobile network infrastructure is shared among several tenants via open APIs. One example would be the case where the infrastructure is owned by an operator and tenants are other operators and over-the-top services such as YouTube and Facebook, as well as vertical industries like automotive and manufacturing industries. 5G NORMA hence provides new business opportunities to operators and in general to infrastructure providers developing a concept based on network slicing introduced by the NGMN white paper. 5G NORMA is going to demonstrate the key innovations via software-based demos and prototypes. We plan to develop demos on multi-service architecture and for software-defined mobile network control. Let's look first to the multi-service architecture demonstrations. The 5G NORMA approach consists in developing software-based demos to analyze and compare different concepts, then select the most promising ones to be implemented in prototypes. The software-based demos combine real-time emulations and 3D visualizations. In this example, we are looking at the Manhattan scenario. The key challenge for 5G is to cope with a variety of services and requirements ranging from high throughput, like HD videos, to critical services characterized by low latency of a few milliseconds and high reliability in the order of 5 nines. All these diverse services will need to be supported by 5G at the same time, and this requires the design of a flexible architecture able to cope with multiple services in an efficient manner. The multi-service adaptation functionality developed in 5G NORMA allows for the architecture to adapt to service type. For example, high-definition video can be downloaded more efficiently with centralized multi-cell interference coordination. Other services, such as autonomous driving or remote control of robots, require the setup of local networks where information is routed locally in order to meet the low latency requirements of a few milliseconds. This is possible by relocating gateway functions from the network to the edge cloud. The native multi-service functionality designed by 5G NORMA allows for the network to support a variety of services at the same time, providing both gain in terms of system capacity for high-throughput services such as HD video and meet low latency requirements of a few milliseconds for services like autonomous driving. The emulator part of the software-based demo computes the real-time performance of different service types, traffic volumes, or backhaul latencies. All these parameters can be modified during the demo, and their impact on performance can be observed in real time. The most promising concepts developed in 5G NORMA will be implemented in prototypes. In the prototype, we will show how the functionality developed in 5G NORMA to support native multi-service allows the architecture to adapt to low latency services. 5G NORMA demos will include a real base station platform. It consists of a base station hardware, which comprises RF and baseband boards, and a customizable software. The base station platform is based on LTE physical layer and protocols enhanced according to 5G radio concepts developed by other 5G PPP projects or standardized within 3GPP. In the 5G NORMA prototype for multi-service architecture, the edge and network clouds are both emulated. The difference in latency between the edge and the network cloud is also emulated. Different services may require different latencies. The functionality developed in 5G NORMA to support native multi-service moves the core network functions, packet gateway and serving gateway, closer to the end user to enable local routing and hence provide low latency. For non-stringent latency services such as video streaming, the virtualized packet gateway and serving gateway functions are in the network cloud. For low latency services such as online gaming, these functions are moved to the edge cloud, closer to the user, and thus reducing latency. Finally, for ultra-low latency services such as autonomous driving, we move the packet gateway and serving gateway functions into the eNode B, enabling local routing, further reducing latency. The second demonstration is about Software-Defined Mobile Network Control, SDMC. With traditional software-defined networking, SDN, control functions are decoupled from the data plane through a well-defined interface and are implemented in software. 5G NORMA follows a similar spirit to SDN when designing the SDMC, but with some substantial differences. SDN implementation is limited to routing or forwarding, while our software-based mobile network control approach focuses on wireless-specific functions in addition to routing. While SDN only controls data plane functions, with SDMC we intend to target also control plane functions, both of which can be placed arbitrarily in the edge cloud or the network cloud. The key idea is that the control functions will be implemented in software in such a way that their operation can be easily modified, thereby changing the behavior of the network without modifying the control functions. Functions considered in 5G NORMA are, among others, channel selection, scheduling, modulation and encoding scheme selection, and power control. The SDMC is part of the 5G NORMA controller. The SDMC module implemented in 5G NORMA thoroughly manages the mobile network, providing flexibility to the operators. In the prototype, we will show how, in case new kinds of services such as low latency ones are requested, for example autonomous driving, the SDMC optimally configures the scheduler according to the targeted service. The new scheduler policies are implemented in software by using a standardized API through the northbound interface of the SDMC. Then, the SDMC hooks them into the 5G base station scheduler using the southbound interface, thus providing the quality of service class required by the new service. In this example, the user requesting autonomous driving service are scheduled with higher priority in order to meet the latency requirements. Thanks to the SDMC developed in 5G NORMA, new wireless control systems are not physically implemented in the base stations anymore, but rather executed on virtual machines deployed in the telecom operator infrastructure cloud. This reduces the complexity of the whole service creation process, both in terms of development and debugging, allowing more services to be created with a much shorter deployment cycle. The project has defined a few key deliverables that contain use cases, requirements, and scenarios relevant to the architecture design are already available in October 2015. The reference architecture used in the project in December 2015. The first and final release of the 5G NORMA architecture are planned for January and September 2017. The evaluation of 5G NORMA architecture based on the KPIs defined in 5G PPP and by the project, as well as the socio-economical analysis, are also in two releases, one in August 2016 and the second one at the end of the project in December 2017. First version of demos and prototypes on multi-service architecture will be released in February 2016 for the Mobile World Congress, the software-defined mobile network control in October 2016, and the final versions of all the demos in November 2017. Thank you for your attention. You can find more information about the project via these links.